Okay, welcome to another short OpenStack astronomy video here. We'll be talking about chapter 25, which is the Milky Way galaxy. So before we start talking about other galaxies, let's see what we know about our own galaxy, and then we can make inferences on others. So the Milky Way galaxy, from our vantage point, it appears kind of like this haze, this strip through the night sky. So if you've ever been out to the desert, going out to Vegas or something, you'll kind of see it. And what that is that we're looking at the galaxy edge on. It's kind of flat like a pancake, and we're looking directly towards the galactic center. We're kind of on the outskirts. So when we look in that direction, it's a lot more dense towards the center. But you'll kind of see this kind of white kind of haze and a lot of dust and stars that are appear in that direction. So William Herschel first and Caroline Herschel first made a model of the galaxy. And so this is their kind of first diagram, a cross-section of the galaxy here. So by doing a census and collecting data on stars and their positions. So they put the sun somewhat kind of close to the center here, and then they mapped out other stars. And again, this is a cross-section of it. Later, Harlow Shapley also made a diagram, and here you could see that the initial model is embedded in here, and he expanded it out a little bit. So positions of stars that went up a bit higher and lower, so extending that model. Today, what we see, or what we know of the Milky Way galaxy, is that it is pretty flat, as we mentioned, and we are located right here in the outskirts. And so when we look towards the center, over here, we're looking towards the galactic center there, and that's kind of that haze that we see. We're kind of in the suburbs, about 27,000 light years or so from the center. The galaxy is about 100. It's about 100,000 light years from end to end, and it consists of the bulge in the center, the disk, which is flat, and then this kind of halo that goes kind of around it. And in that halo, we have a lot of globular clusters. This is an artist's rendition here of a kind of angled view here. So you could see the bulge, the disk, then the halo with globular clusters. And in the actual disk, we have these spiral arms. And those are kind of tend to be more bluish in color. We don't have a long enough selfie stick to take a picture of the Milky Way, so every time you see an image of one, it's typically an artist's rendition or another spiral galaxy that is similar. So let's talk about the spiral structure. And so the spiral structure is very interesting. It has a lot of dust, a lot of that interstellar medium there. And it's bluish in color, so indication of a new star formation in the spiral here. So we look at some galaxies that you could have an unbarreled, like our Milky Way galaxy, so spirals kind of starting from the center there, or barreled, where you kind of have this long line and then just minimal spirals there as well. But either way, in the arms there, in the spirals, we see it that it's more bluish in color. So we see this kind of ionized disk here, this nebula, and that bluish color again indicates star formation. So in the spiral, we have ongoing star formation. In the halo up here, where there's these globular clusters, those are more kind of yellow reddish in color, which indicates older stars, so no star formation happening there. So as the galaxy spins around, you have these gas that's contracting, right, forming new stars. But as it spins around, you have the gases also kind of get dispersed. So you start seeing these spirals that tend to start forming there. And so as these stars go around in the spiral, those blue stars are short-lived, and they typically don't make it all the way around. It takes the sun about 250 million years to go all the way around. So these stars won't make the full trip around. And so you have these stars, and then they'll tend to die out, and that'll be the end of that spiral arm. And then you'll have these new waves of gases that come through as it rotates that creates new stars. And so that's how those spirals end up forming. It's just new stars that keep forming there, and it keeps that bluish color. And so we could see that here. So again, as these gases go, you have a cluster of stars that form here. Let me pick a different color. So starting here, a cluster of stars that form, and as they make their way around through, then they end up dying about there. They fade out. And so they don't get to go all the way around. And so again, that creates those spirals there. So these gas clouds get kind of squeezed. They move into that spiral arm, and then that triggers that star formation. And so young stars flow out of the spiral arms there. So what do we know about the mass of the galaxy? So we see, star formation. There's ongoing star formation happening. But how much mass is there, right? How long could we expect that to happen here? And so what happens when we look at the rotation of the galaxy is a couple of cases here. If we look at orbits of planets, if you recall the laws of planetary rotation here, that as planets are closer, they tend to go faster, and as they're further away, they go slower. So we end up with a curve that tends to kind of go downwards here. So starting up high, then starts plateauing down as we go further out. And so this is how the solar system, we see velocities within the solar system. But what if we consider something that rotates kind of uniformly here, like a merry-go-round? Well, as things orbit around here, if you are, let's just say here in position A, here we go, make this a little bit, there we go. So if you're in position A here, now when you orbit around, you're going to make a fairly small circle. If you're over here in position, let's go with C over here, and you go all the way around, that's going to be a larger circle. But these guys are on the same line here, so they have to move together. So in this case, the further out you are, the faster you're going to go, and the closer to the center, the slower you go. And you end up with a graph that increases this way here. So the question is, how does the galaxy orbit around? If we follow stars around, is it more like within the solar system, or something that's a bit more uniform? And what we see is that actually neither. We see that they tend to kind of increase, and then they plateau off there. So the rotation curve of the Milky Way kind of flattened out with distance here. And so what this indicates is that there must be more mass spread out in the solar system than we're accounting for. And so a couple of things here is either our mathematics, right, our models are off here, or there's something else there. And this is what we call dark matter. Dark because it doesn't really interact with ordinary matter in the same fashion, so difficult to see, and also because we don't really understand it. So that dark matter, and what we assume is that there should be more dark matter spread out around the halo of the galaxy for it to rotate in the fashion that it does. So this is the luminous matter where we could see kind of, visually what we see. But by these models and velocities, it indicates that we should have a lot more matter in the outskirts there. So a lot of what we call this dark matter. Okay, so what do we actually see in the center of the galaxy? And so when we look at the center, we end up seeing a lot of radio emissions, so hot ionized gas that's coming out from the center, these huge kind of gas streams that end up being ejected outwards. We also see that in towards the center, stars are moving at a extremely high velocity, orbiting around some center of mass. And we're able to track some of the orbits of these stars, and they're going extremely fast, which indicates something with a large amount of mass is at the center. And we're talking something extraordinary about 4 million solar masses. Now, when we talk about black holes, stellar black holes, we're talking star size, 20 solar masses, 30 solar masses. We're talking about something now the size of 4 million. So it suggests that there's something massive there, and we believe that it's a supermassive black hole at the center of the galaxy. So we see huge X-ray flares coming out from the center. This suggests these tidal forces, and again, more evidence suggesting that there is a large black hole in the center. We're not able to actually see the black hole, but we could see accretion disk around there, and we could see that it seems to tear apart chunks of matter that are about to kind of fall in. So all of this evidence suggesting a large black hole at the center. And so what do we see now in the stellar populations in the galaxy here? So how do stars just move around, in the plane of the spiral galaxy here? And so what we see is that around the halo, orbits are kind of just random, but right around the actual disk, where the spiral is, we see that stars tend to kind of stay right on that plane, but they do hover up and down kind of like a merry-go-round. And of course, around the center in the bulge, it gets a little chaotic with stars orbiting in all kind of random directions there. So the galaxy here, again, when we talk about formation of it, huge clouds of gas, right, start contracting. And we see that initially that huge cloud, stars started forming. And so in the halo, you have some earlier star formation, these globular clusters. And then as it's started rotating and settling down on the plane, you have these older globular clusters that are kind of in the halo there. But now all the dust has settled on the disk, and you get those spirals with ongoing star formation. And so we see that in the disk here, heavier elements, again, because we have more generations of stars there. And then in the halo, those globular clusters. And so you see that in the halo, you have less heavy elements. So again, suggesting much younger stars or earlier generation of stars there that are going to be that are much older, right? And those that are newer now, after supernovas happen on the actual disk, are going to be heavier elements, so newer stars, and we see that about 2% of those heavier elements. Here's an image of kind of the galactic halo here. Again, things orbiting around the outskirts. You have that disk there, and then around the bulge, again, a lot of activity there. And so this kind of looks at some of these kind of tidal streams might look like from the Milky Way galaxy here, as some of these dwarf galaxies kind of pass around it. The Milky Way, we believe, has consumed several dwarf galaxies around it. And here we see a globular cluster, again, a dwarf galaxy that is next to us. And here is an artist's rendition of the ultimate fate of the Milky Way colliding with the Andromeda galaxy. So eventually those will collide. So what we see ultimately is that galaxies tend to consume each other. Our Milky Way galaxy has consumed some dwarf galaxies. The Andromeda, which is much larger, will eventually, we're on a collision course, will consume us. And since we believe there are black holes at the center of each galaxy, really, when one galaxy consumes another, we're really looking at a merger of these supermassive black holes. So as we study cosmology, the structure of the universe, we have to look at how galaxies are attracted, how they end up colliding with one another, which in turn is really looking at how these supermassive black holes merge with one another. So we'll talk a bit more about that in the next section. This is kind of what we know about our Milky Way galaxy, some of the characteristics, and then we'll start inferring that to some of the other galaxies.